In this video, I will walk through a metallurgical driven process to help you prevent forging defects. What follows is a step-by-step explanation based on practical observation and process experience. Hi, I am Rahul Agarwal, founder and managing director of Prestech Forgings and Engineering Private Limited. Over the years, I have reviewed hundreds of forging defects like cracks, laps, scale pits, inclusions and whatnot. Most are not random, they are results of process gap that can be addressed systematically. Now let's break it down. Step number 1. Start with the right raw material. Let me tell you something, many people miss that. Forging defects often begin from before the forging even starts. They begin in the raw material yard. If the raw material is chemically inconsistent, contaminated or structurally poor, the risk of downstream failure increases sharply. Material verification should never be an optional case. Every heat, every batch must be traceable and verified. This means reviewing with mill test certificates, conducting spectrochemical analysis to confirm that the mill TC and the chemical composition matches, checking grain size, inclusions, surface condition, using macro etching to observe internal grain flow when needed. It can also be ultrasonic tested the bars to find any internal flaws. Common consequences of poor quality material include inclusions turning into internal cracks, surface defects leading to laps and folds, chemical issues affecting heat treatment responses. Material quality is the foundation. It influences everything else that follows. All the process that follows will have a significant influence from the raw material stage itself. Step number 2. Control the heating process. Heating is not a preparation in forging, it is a part of forging. Inconsistent or improper heating can lead to grain coarsening from overheating, incomplete material flow from underheating, internal stress from uneven thermal distribution. Uneven thermal distribution means the core there is no heat and on the surface the billet is heated to 1200. Billets must be heated uniformly, both surface and core. Controlled furnaces with accurate soak time tracking will help avoid thermal gradients that cause distortion or rejection later. Heating should be approached with precision. It's better to use an induction billet heaters with a 3-way accept reject system. Maintain validated temperature zones. Avoid flame based on manual heating methods for critical parts. Treat temperature and soak time as a process parameters, not estimates. Uncontrolled heating compromises the forging process and before the deformation happens. Step number 3. Optimization of die design and alignment. Most people blame the material or the forging press or hammers, but I have found that many forging defects are born in the die. Die related defects are common but often misdiagnosed. Laps, folds, cold shuts and underfills frequently stem from flawed die geometry or poor alignment of the bottom die and the top die. Key preventive measures includes validating the draft angles, radii and flash land sizes, running metal flow simulations to anticipate material behavior inside the die, ensuring die halves are aligned and balanced with precision tooling. Even a minor mismatch, 1 mm or less, can result in visible and hidden defects. Die maintenance is equally critical. Monitor for where that could lead to dimensional drift. Inspect for surface erosion that affects finish of the quality. Track alignment consistency throughout production cycles. Always maintain a tool history card. Tooling must be maintained with the same rigor as the forging process itself. Step number 4. Apply precise heat treatment. Heat treatment determines the final mechanical properties of a forged parts. Each process, like normalizing, annealing, quenching, tempering, has a specific purpose based on material and part dimensions or geometry. Precision in this step is very much required. This is the most important step for the performance of the forged component. Calibrated furnace with uniform heat zones, controlled heating, cooling rates are very essential to avoid thermal stress. Accurate soak durations aligned with part thickness. Defects associated with poor heat treatment include decarburization, loss of surface hardness, wrapping or cracking from rapid or uneven cooling, residual stress and brittleness from improper tempering. Post-treatment validation should include microstructural analysis, hardness testing, dimensional stability checks. Sometimes there is a distortion in the dimension after the heat treatment. This stage is not just about achieving hardness, it's about ensuring performance integrity. Step number 5. Use in-process inspection. Inspection is not a checkpoint, it is a mindset. I do not believe in inspecting only at the end of the line, because by that time the material is already wasted, the cost is already locked, the customer is already waiting, and the main impact is to the customer. Final inspection alone is insufficient for quality control. Process integrated inspection is more effective in preventing batch level defects. In-process checks help catch issues early. We can do ultrasonic testing for internal flaws, magnetic particle or dye penetrate testing for any surface cracks, visual audits for flow lines, laps or underfills. Operators must be trained to identify abnormalities mid-process, not just after production. If the operator identifies any issues in the beginning or while forging, it can be prevented at that stage itself. Critical process data to be logged into includes forging and forging furnace and forging temperature, press load and stroke consistency, tool condition during the run. Inspection should support learning, not just deduction. This learning will help to prevent it in the future. Documenting these insights help reduce future errors and improves root cause traceability. And let me tell you one thing, clients remembers that. When they know you check during, not just after, you move from being a vendor to being a part of their process. Step number 6. Since you have done in process, that doesn't mean that you avoid final inspection. Final inspection before dispatch is the step number 6. This is the last opportunity to verify conformance before the part enters the next system or goes to the customer place. Final inspection should include dimensional check using calibrated gauges and instruments, hardness testing to validate heat treatment effectiveness, surface checks for cracks, burrs, oxidization or any type of scaling or surface defects. But inspection is more than a checklist. Patterns must be observed. Does this batch show variation compared to the previous one? Is inspection time increasing, indicating a deeper issue? And borderline parts becoming more frequent? If additional effort is needed to pass inspection, upstream steps should be reviewed and go back to the basic: heating, tooling, material quality. Final inspection is not just about passing the material, it is about confirming readiness for real world performance. If this video helped you rethink quality from the ground up, share it with a colleague or send it to your supplier. Better conversations leads to better components. Thank you. See you in my next video.